Welcome everyone. This video is of our work in database graph analytic with recursive Sparqal. So let's start with an example. Suppose that we have the citation network of articles on a topic of interest, for instance, the semantic web, and we want to find the most important articles and the most prominent authors in the area. And of course, the citation network is available as an RDF dataset. So to achieve this task, what we could do is to calculate the page rank for each article, then get the authors of such articles, and then aggregate our results. But stop, wait a minute. Page rank and RDF. So how can we compute the page rank algorithm over an RDF graph? We have many ideas of how to do this. For instance, the first one is to load the citation network with a programming language such as Python or Julia, or with a graph analytics frameworks, for instance, GraphX and Giraffe, and then compute page rank. But there is a question here that how can we incorporate the information about the authors then after computing the page rank algorithm? And what if I need to do more queries? Is there an easy way to integrate the results with the RDF data? Well, another idea is to use a database that supports some analytic feature such as Neo4j and Gremlin. But the problem here is that I need to transform my data to a property graph model, and this implies a lot of work that maybe I don't want to do. And then another problem is, what if I don't have access to the dataset and I just have access to the Sparqal endpoint? Is there a way then to achieve this task? Yes, of course, there are many ways to do this, but is there a straightforward way to achieve this task? In our opinion, no, there isn't. This is why we are proposing Sparqal. This language is Sparqal Protocol and RDF query and analytics language. And this language is a recursive extension to Sparqal that supports graph querylytics. Here we are introducing a new concept which is called querylytics, and we refer to querylytics to tasks that combine querying and analytics on graph. This is what we want to do in the example, because we need to do a query to obtain the citation network and to aggregate results, but also we need to compute page rank, which is a graph analytics procedure. Now we will continue with the preliminaries for this talk. So first, we want to review all the existing technologies for querying graphs or doing graph analytics. So here we have a lot of frameworks, database management system, programming languages. Some of them are RDF friendly. Some of them may load RDF graphs, but are not designed for that purpose. So we start with DBMS. We have RDF systems like Gina and Virtuoso. They are designed for querying RDF graphs, but they lack of analytic features. Then we have relational DBMS like Postgres. Of course, Postgres is not RDF friendly, but Postgres can run stored procedures. You can do anything with stored procedures. Then we move to things like Gremlin or Neo4j. They are designed for working with the property graph model. So maybe sometimes we don't want to move our RDF data to the property graph. But here we highlight Neo4j because Neo4j has a new GTS module that contains several graph analytic algorithms, and you can query the graph and also join the results with the graph analytic procedures. That finally is what we want to do. So if a property graph model is looking in that direction, maybe the RDF model has to look in that way too. Then we have graph analytic frameworks, and of course they can do several graph analytic algorithms, but they are not designed for querying graphs. So maybe it's difficult to incorporate RDF data doing queries and integrate the results with the procedures that these frameworks can run. Finally, we have programming languages. We can do anything with programming languages, but maybe, I don't know, using Python to solve these problems is more work than the one that we want to do. So then there is a gap in the middle that we want to fill with Sparqal, because we firmly believe that we need techniques that allow us to do graph analytics over RDF graphs, but also allow us to use the query features of Sparqal. Now we know that we use the usual syntax of Sparqal, but we recall that the result of a Sparqal query is a solution sequence. We can think of it as a table, and we also recall the existence of the values clause. The values allow us to fix some solution sequence within a Sparqal query. And for instance, in this query, we have a triple pattern, and we are joining the results with the solution sequence that the values is exposing. And finally, we are ready to present Sparqal. We will start with an example. Suppose that there is a concert close to the Palermo station in Buenos Aires, but line C is closed due to a strike. So we want to know all the reachable stations from Palermo without considering the line C station. To illustrate how Sparqal works, we will compute this task with a Sparqal procedure over the graph of Wikidata. So this is the procedure. We are going to go step by step. At the beginning of the procedure, we are computing all the stations adjacent to Palermo, but that are not part of the line C. And also, we define this variable called reachable, and we store in reachable the solution sequence generated by the query. After that, we start a loop. At the loop, we do a query that uses the solution sequence stored in the variable reachable. Note that we are using our qvalues clause, which is like a values that expose the solution sequence of the corresponding variable. In this case, we are using qvalues of the variable reachable that we defined before. And then we are computing the adjacent stations of all the stations stored in the variable reachable, but again, we are excluding the adjacent stations that are part of the line C. And here we have the recursive part. We define the variable reachable again, and note that at the query, we are using the qvalues of the variable reachable. So we are defining the variable reachable in terms of itself. Thus, in each iteration of the loop, we are adding reachable stations from Palermo. First station at distance 2, then at distance 3, and so on. This is because here we are doing the union of the new adjacent stations with the previous stations stored in the variable reachable. We also are removing duplicated stations. And we stop when we find a fixed point. That means that the variable reachable does not change from iteration to iteration. And at the end, we return the corresponding solution sequence that is storing the result that we need. Then the statement that we are adding to Sparqal are the following. So the first statement is the assign statement. The keyword here is let. We can define variables and we assign to these variables the solution sequence of the Sparqal queries. An important thing here is that the Sparqal query may use the qvalues clause. So the qvalues statement is something that allows us to expose the solution sequence that are stored in our variables. Then we have the loop statement that allows us to repeat certain actions until some condition is satisfied. The conditions are times I. Here we execute a loop of fixed number of iterations. We stop at the if iteration. We have the condition fixed point. That is the one that we use in the example. We execute the loop until the Sparqal variable that we are using inside fixed point does not change in 2 consecutive iterations. And finally, we have another condition with this an ask query. We can execute a loop until a Sparqal ask query returns true. And of course, this query may use the qvalues clause. And as we see at the example, at the end of a Sparqal procedure, we have a return statement that returns the solution sequence stored in the corresponding variable. And every Sparqal procedure must end with a return. And now an interesting question is to understand what is the expressive power of Sparqal. So we studied this problem and we found that Sparqal is Turing complete. Basically, because we can create new values with bind operator, we have arithmetic functions, and we have also a loop. Then we can simulate a Turing machine. And what if we don't invent new values? Then we have the following proposition. The evaluation problem of Sparqal procedures that do not invent new values is p-space complete. And now, since we studied how Sparqal works, we will give a more complex example. We will recall the first example. We will compute the p-index of the authors according to the citation network of articles related to the Zika virus. And we think that this is a good example of what querylytic is, because first we have to generate the citation network, then we have to compute PageRank, and afterwards we have to join the results of the graph analytics algorithm with the database to get the answer that we need. So we start generating the citation network and defining some variables. So this is the first part of the procedure. At the first step, we are generating the citation network of articles related to the Zika virus. We're storing pair of nodes, and then we can think about this variable as a variable that stores a directed graph. In this case, we are working with papers where one paper cites another one. We have to store all the nodes of the graph in this variable. We have to store the number of nodes in the graph. For computing PageRank, we need the out degree of each node. So we are defining a variable which store pairs, the node, and the out degree of such nodes. And we also define the initial PageRank, which is equals to 1 divided by the number of nodes in the graph. Then we have the part 2, where we start to iterate to compute the PageRank of each node. This is the loop that we need. And for simplicity, we're executing this loop 10 times. The first step of the loop is where each node shares its PageRank to its neighbor. And each node has to divide the PageRank in equals part to each one of the neighbors. After that, we have to compute the total rank that is not shared with edges. We recall that this is needed, for instance, for nodes that are isolated in the graph. And finally, we have to override the page rank of each node. And the last part of this algorithm is join the results with the authors. So this is easy since we have a variable that stores the page rank. We can write a query that goes to the database and join the results of the page rank algorithm and the triples at the database. And finally, we return the index of each author. Now, we will show a technique that is useful to compute Sparqal procedures. Of course, there is a straightforward way to implement our language, and this involves replacing the Q values for values clause, which is part of Sparqal, and put into the values clause the corresponding solution sequence. But we will show at the experimental section that this alternative does not scale for layer graphs, mainly because this can generate long query strings. Then we define a recursive algebra for graphs that can also express querylytics, and we will show this approach with an example. So consider the query that gave us the citation network of the PageRank example. We say that this represents a directed graph. Then instead of storing the solution sequence, what we do is to replace it with a construct. Then we create a named graph called example SIGA in our database. And every time we refer to the variable of the citation network, instead of going to the solution sequence, we will use this named graph. Also, consider the solution sequence that contains the out degree of each node. We can think this about adding a property to each node. So what we do is to create a graph that has the node and the degree associated with it. And again, we store this as a named graph. Then in general terms, we replace the solution sequence that represent directed graphs by named graphs. And we also replace the solution sequences that store properties for each node. And now every Q-value sentence is handled using the named graph instead of the solution sequence. And note that named graph can be updated in the same way that we updated Sparqal variables. Then every procedure of Sparqal can be compiled into expressions using this algebra of updates. And the idea of doing this is that we can benefit from the indexes that the database gives to each named graph. Note that arbitrary solution sequences cannot be indexed with the standard indexes of RDF database. Also, a general solution with graph updates is possible, but this implies reifying any Sparqal solution sequence. And of course, this approach is useful to run several graph analytics algorithms. Now at the experimental section, we are going to show that our approach is feasible in practice, and also how this graph updates approach helps to improve the performance of our procedures dramatically. So we implemented both approaches, the values and the graph updates, and we tried with 5 graph analytics procedures. The algorithms that we try are BFS, local cluster coefficient, shortest path PageRank, and weakly connected components. And then the first benchmark that we try is a benchmark designed by us, where we created 6 construct queries that gave us subgraphs from the truth RDF dump of Wikidata. These are the graphs, these are the subgraphs that we try. And as we see, each one of our algorithms was computed in a reasonable amount of time. We claim that our approach is useful for interactive use with small to medium scale graphs, but what happened with larger graphs? Here we try with the Graphalytics benchmark, and as we see, the values approach didn't scale for this size, but the graph updates approach that we implemented over Apache Gina and Virtuoso took a reasonable amount of time considering the scale of the graph. Then as a conclusion of this part of the experiment, we see that the values approach doesn't scale, but the performance issues are alleviated by the graph updates approach. So what did we learn? Well, we believe that the combination of graph queries and analytics is a natural one, and we're starting to see first approaches in other data models, such as Neo4j and the graph data science model, that are doing what we call querylytics. So we firmly believe that RDF databases have to go in this direction too. So when we propose Sparqal, we are trying to propose a first language that goes in this direction. And for us, a key research challenge for the future is to understand how to optimize these procedures. A way to improve this is to understand that solution sequences aren't necessarily triples, so RDF databases may need more general indexes than the current ones. And also, we believe that our graph updates approach can be useful to compile Sparqal procedures to linear algebra languages and then delegate the procedures to the GPU. So this is our video, I hope you enjoy it. Thank you.